The power and functions of a coil in electronics. At its core, a coil or inductor stores energy in a magnetic field when current passes through it. That's its superpower. Unlike capacitors, which store energy in an electric field, coils deal with magnetism. This ability gives them authority over currents and signals, making them vital in power systems, communication, and filtering. Energy storage, magnetic field. When current flows through a coil of wire, something almost magical happens. The electrons moving to the wire generate a magnetic field that surrounds a coil. This field isn't just invisible fluff in the air. It's a reservoir of energy. Think of it like this. A capacitor holds energy as an electric tension between its plates. A coil holds energy in the embrace of its magnetic field. As long as current flows, that magnetic field is alive, wrapping around the coil like invisible rings of power. If the current suddenly decreases, the coil resists by releasing the stored magnetic energy back into the circuit, keeping the current from dropping too abruptly. This is why engineers often call the inductor coil reluctant to change. It doesn't like sudden disruptions. Its magnetic field acts like a cushion, ensuring smoother energy flow. Real-world examples. In power supplies, coils store energy during one part of the cycle and release in another, stabilizing the output. In electric cars, large inductors help manage the flow of power between the battery and the motor efficiently. In wireless chargers, energy stored in one coil's magnetic field is transferred to another coil nearby. Backhand index pointing right in essence. The coil's true power is its ability to capture electricity in the language of magnetism and then give it back when the circuit needs it most. Filtering, smoothing currents and signals. Electricity in real life is messy. It doesn't flow like a calm river. It's more like a stormy sea, full of ripples, spikes, and noise. This is a big problem in sensitive devices like your phone, radio, or computer, where even tiny disturbances can throw the whole system off. This is where the coil steps in. Because of its inductive nature, a coil doesn't like rapid changes in current. It resists them. In doing so, it smooths out the jagged edges of electrical flow. Two main roles in filtering. Power supply smoothing. After electricity is converted from AC, alternating current, to DC, direct current, it still has ripples left over. A coil, often paired with capacitor, acts like a damper, calming the current into a steady, smooth flow so your devices don't fry or glitch. Signal filtering. In radios, audio systems, and communication circuits, coils act like bouncers at the door. They let certain frequencies through while blocking others. This is how you can tune into one radio station without hearing all the others shouting over it. Everyday picture. Imagine drinking water from a tap without a filter. You get particles, dirt, and who knows what else. Add a filter, and suddenly it's clear, clean, and safe. That's exactly what a coil does for electricity. It filters out the noise, leaving only what the circuit actually needs. Backhand index pointing right, so in short, the coil is the noise-canceling headphone of electronics, turning turbulent, messy currents into smooth, reliable energy and signals. Inductive reactance, impedance control. When DC direct current flows through a coil, it's happy. Steady current, steady magnetic field, no complaints. But when AC alternating current comes in, things get interesting. AC is always changing direction and speed. Each time it changes, the coil's magnetic field has to build up and collapse again. That takes effort, and the coil resists. This resistance isn't ordinary resistance, like heat from a resistor. It's a dynamic opposition called inductive reactance. The faster the AC changes higher frequency, the harder the coil pushes back. In other words, low-frequency signals, the coil lets them pass more easily. High-frequency signals, the coil blocks them like a stubborn gatekeeper. This gives coils the power to control, filter, and shape signals, acting as frequency-sensitive valves in electronics. Practical uses. Frequency selection. In audio equipment, coils help separate bass from treble, ensuring your subwoofer doesn't try to sing soprano. Impedance matching. In communication systems, coils ensure that antennas and transmitters speak the same language, reducing wasted power. AC current limiting. At high frequencies, coils naturally choke the current, protecting sensitive circuits. Everyday analogy. Think of a coil like a revolving door in a busy building. If people walk slowly, low frequency, they glide through. If people try to sprint, high frequency, the door resists, slowing them down. That's inductive reactance, a frequency-dependent resistance that gives coils the power to control the flow of AC like a seasoned doorman. Back-end index pointing right, so the coil's power here is in discipline. It doesn't just let any signal through. It measures, resists, and decides it gets passage based on rhythm and speed. Tuning and frequency selection. A coil's secret talent shows when it teams up with a capacitor. Together, they form what's called a resonance circuit or LC circuit. This pair can be tuned to ring at a specific frequency, just like a guitar string vibrates at a particular pitch when plucked. When that happens, the circuit either passes signals at its resonant frequency or blocks signals that don't match. This makes coils the backbone of radios, TVs, and communication systems. How it works in practice. Radios and TVs. When you spin the dial or hit scan, you're actually adjusting the coil plus capacitor combo to resonate at a station's frequency. Without the coil, all you'd hear is chaotic static from every channel at once. Wireless communication. In cell phones and Wi-Fi devices, coils help select the right frequencies from a crowded spectrum, so your call isn't hijacked by your neighbor's cat video stream. Musical filtering. Audio systems use coils to separate deep bass from high treble, ensuring each speaker only sings its part in the performance. Everyday analogy. Think of the world as a giant room full of people talking at once, every frequency buzzing together. A coil paired with capacitor is like a radio tuned to a friend's exact voice. It zeroes in and says, "That's the one I want." Everyone else, hush. Back-end index pointing right, so in essence, the coil gives electronics the power of choice. Instead of drowning in noise, circuits can focus, select, and tune into exactly what they need. Energy transfer, transformers, and coupling. One coil on its own is powerful, but put two coils close together, and something remarkable happens. Energy can jump from one to the other, not by wires, but by magnetic fields. This process is called mutual induction, and it's the principle behind transformers, wireless chargers, and even some medical devices. How it works. When an alternating current flows through the first coil, the primary, it creates a changing magnetic field. That field cuts through the nearby second coil, the secondary, and by induction, it generates a current there. Boom! Energy has moved without direct contact. This isn't sci-fi. It's the everyday magic powering your devices. Practical applications. Transformers. Transformers use paired coils to step voltage up or down. That's why electricity can travel across continents at high voltage. Then safely power your phone charger 5V. Wireless charging. Your phone sits on a pad, no wires attached. Coils inside the charger, and inside your phone exchange energy through magnetic coupling. Signal coupling. In audio systems, coils pass signals between circuits without direct electrical connection, reducing noise and interference. Isolation. Coils and transformers also act as guardians, isolating one part of the circuit from another for safety. Everyday analogy. Picture two dancers in perfect sync. One moves, and the other mirrors the steps, even without touching, because the rhythm magnetic field connects them. That's exactly what paired coils do. They transfer energy by shared rhythm, not by direct contact. Back-end index pointing right, so in essence, the coil's power here is communication. It teaches electricity to leap across gaps, to transform, and to adapt, making long-distance power grids, wireless charging, and clear signal transfer possible. Choking, current limiting in circuits. A coil doesn't just store energy or select frequencies. It can also block, limit, or choke certain currents. That's why inductors designed for this purpose are literally called chokes. Here's the key. A choke allows steady DC, direct current, to flow through easily. But when it comes to AC alternating current, especially high-frequency signals or noise, the choke resists blocking or reducing them. It's like a filter that says, clean, steady flow, come right in. Noisy, high-frequency chaos, you're not welcome here. Practical uses of choking. Noise suppression. In power supplies, chokes stop high-frequency interference from sneaking into sensitive circuits. Protecting devices. Chokes limit sudden surges of current, shielding delicate components from spikes that could cause damage. Signal filtering. They act as guards in communication systems, preventing unwanted frequencies from corrupting the signal. Lighting and motors. Chokes help regulate current flow in fluorescent lamps and motors, ensuring they start and run smoothly. Everyday analogy. Imagine a nightclub with a bouncer at the door. Regular guests, steady DC current, are waved in. Rowdy troublemakers, high-frequency noise, get stopped at the entrance. That's a choke. It keeps the environment inside safe and stable. Backhand index pointing right. So, in essence, choking is a coil's defensive power. It protects circuits from noise, chaos, and surges, ensuring only the right kind of current passes through. White heavy check mark. Now you've got all 6 powers of the coil explained. Energy storage, magnetic field. Filtering, smoothing currents and signals. Inductive reactance, impedance control. Tuning and frequency selection. Energy transfer, transformers and coupling. Choking, current limiting in circuits. In short, the power of the coil lies in its control over magnetic fields, and its functions range from storing and filtering energy to selecting, transferring, and protecting signals and power.